So in the last lecture, we saw that in object-oriented programming, we define a data type through a template called a class, which defines the internal data implementation and the functions that we use to manipulate the data type. And then we create instances of this data type as objects. So we saw a skeleton implementation of a heap. So this had a special function called init, okay, which was used to create the heap. And then we had functions insert and delete. Now, one thing which we did not explain is this argument self that runs through this. So this is a convention which we have in Python, that every function defined inside a class should have as its first parameter the name self. Now it need not be called self, but it's less confusing to always call it self. So let's just assume that this parameter is always there and it's called self. Now what is self? Self is a name that is used inside the class to refer to the object that we are currently looking at. So for instance, if we are dealing with this heap h, when we say h.insert, then this insert is using the value 17. So 17 is the value x which is being passed to insert, and h is the value on which the 17 should be added, and that is a name for self. So self, in other words, tells the function which object it is operating on itself. So it's a name to itself because you're telling a function, an object, a heap h, insert 17 into yourself. So in that sense, my values are denoted by self, and inside a heap we can maybe refer to other heaps. Okay, we will see a little later that we can take one value and refer to another value. So there will be my values and there will be other values. So my values are always implicitly called self because that's the one that is typically manipulated by a function. So to make this a little clearer, let's look at a slightly simpler example than heaps to get all the notation and the terminology correct for us. So our first example is just a representation of a point xy. So we're just thinking about a normal coordinate system where we have the x-axis, the y-axis, and therefore a given point is given some coordinate like a comma p. So this is a point whose x coordinate is a and y coordinate is b. This is a familiar concept that all of you must have seen in mathematics at some point. So we want to associate with such an object two quantities, the x coordinate and the y coordinate, and this is set up by the init function by passing the values a and b that you want the point to have. And now we have within the point we have these two attributes x and y. Okay? So every point looks like this. It has an x value and a y value, and this x value is something and the y value is something. And if we change this x and y value, then the point shifts around from one place to another. Now in order to designate that the x and y belong to this point and no other, we prefix it by self. So self dot x refers to the x value within this point, myself. Self dot y is the y value within myself. If we have a generic point p, then we have p dot x, p dot y. These will refer to the values x and y, the names x and y associated with the point p. So inside the class definition, self refers to the value of the attribute or the name within this particular object. Now this particular object changes as we move from one object to another, but for every object, self is itself. So for P1, if I tell something about P1, in the context of P1, self is P1. If I have a different point P2, in the context of P2, self is P2. Okay? So this is an important thing. So just remember that every function inside a class definition should always have the first argument as self and then the actual argument. So init in this case takes two arguments, but we always insert a third argument. So let's look at how this works. For instance, if we say p is equal to 0.32, then 3 will be passed as a and 2 will be passed as b, and this will set up a point that we have drawn here, okay, which internally is represented as self.x is 3 and self.y is 2. Now here is a slightly different function. It takes a point and shifts it. So we want to say shift this to 3 plus delta x and 4 plus delta y. So this function we call translate. So it takes the amount of shift as the argument, delta x and delta y. And as usual, we are always providing self as the default first argument. Okay? So it just keep this in mind. Every Python function, every Python class, if you want to use a function in the object-oriented style, the first argument must necessarily be self and then the real arguments. So what do we want to do when we want to translate a point? We want to take self.x, right, and move it to self.x plus the value delta x. Right? So we want self.x plus delta x. Now this is a very common paradigm in Python and other programming languages where you want to take a name, say z, and then you want to shift it by some amount, say z plus 6 or z is equal to z minus 6. So whenever we have this kind of a thing where the same name is being updated, there is a short form where we can combine the operation with the assignment. So self.x plus equal to delta x is just a shortcut in Python for self.x equal to self.x plus delta x. It means that implicitly the name on the left is the first argument to the operation mentioned along with the assignment operation. Okay, so this is a very convenient shortcut. It allows us to save some typing. So instead of writing self.x equal to self.x with delta x, we just write self.x plus equal to delta x. So this shifts the x coordinate of the current point by the argument provided to translate. Similarly, self.y plus equal to delta y will shift the argument by the amount provided by delta y. So for instance, now if we say p dot translate to 1, then we get a new point which is 3 plus 2 5 for the x coordinate and 2 plus 1 3, right? So this 3 plus 2 gives us 5 and 2 plus 1 gives us 3. So this shifts the point from 3 to 5 3. Right? So this is how we define these internal. So the internal implementation is defined inside the init function. This is the function that is called when the point is set up, and this associates these internal names x and y with the object. So this is where the implementation really gets set up. And then the functions that we define externally, like translate, manipulate this internal representation in an appropriate way so that it changes consistently with what you expect the functions to do. So let's look at a different function. So supposing we want to compute the distance of a point from the origin. So we want to know what is this distance. So this distance by Pythagoras' theorem is nothing but the square root of x squared plus y squared, right? So remember, this is like the hypotenuse of a right angle triangle. So you take x squared plus y squared square root and you get d. So if we want the distance of a point, we don't give it any arguments, but we always have this default argument self, right? So we want to know what is the distance from 0 0 to the current point. So we would say something like, in our earlier case, p is equal to point, say 3 comma 4, and then we would say p dot o distance to get its distance. So maybe we would assign this to a name. Let us not call it, say we might assign this to a name like n, right? So when we do this, it will look at the current value of self.x, the current value of self.y, square them, add them, and take the square root. Now one thing to remember is that actually square root is not a function available by default in Python, so you actually have to import the math library. So at the top of your class definition, you should have remembered to write from math import star. Okay, so assuming that we have done that, then square root is defined. So this is a typical function which returns some information about the point. The earlier function just translated the point, didn't tell us anything. This is a function that returns some information about the point. Now, if O distance is something that we need to do often, then maybe it's useful to just keep the point in a different representation. So you may remember, or you may have seen somewhere in high school mathematics, that if you take a point xy, then an alternative way of representing where this point is to actually use polar coordinates. So you can keep this distance and you can keep this angle. So if I have r and theta, it's the same information as keeping x and y. So the connection between the two is that x is r cos theta, where cos is a trigonometric cosine function, y is equal to r sine theta. Okay? And on the other hand, if I have x and y, then I can recover r as we just did for O distance. It's the square root of x squared plus y squared. And theta, so y by x is actually, if you divide y by x, you get tan of theta. Just because it's sine divided by cos and the r cancels. So y by x is tan theta. So theta is the tan inverse of y by x. So now, speaking of changing implementation, we could change our implementation so that we don't keep the internal representation in terms of x and y. We actually keep it in terms of r and theta, but the functions remain the same. So for instance, we could take the earlier definition and change it. So we again pass it x and y. So from the user's perspective, the user believes that the point is defined in terms of the x and y coordinate. But instead of using a and b as the argument directly to set up the point, we first set up the r, the radius, okay, by taking the square root of a squared plus b squared. And then depending, so we want to divide b by a, right? But if a is 0, then we have a special case, b by a will give us an error. So if a is 0, we set the angle to be 0. Otherwise, this is the Python function in the math library for tan inverse, arctan. We set theta to be the arctan of b minus a, b divided by a, right? So we internally manipulate the xy version to r theta using the same formula that we had shown before, which is that r is square root of x squared plus y squared and theta is tan inverse of y by x. The only thing we have to take care is when x is equal to 0, we have to manually set theta to 0. So now internally we are now keeping self.r and self.theta. We are not keeping self.x and self.y. So this is useful because if we want the O distance, the origin distance, we just have to return the R value, we don't do any computation. So in other words, if we are going to use O distance very often, then it is better to use the calculation square root a squared plus b squared once at the beginning when we set up the point and just return the R value without any calculation whenever we want the distance from the origin. So this might be a requirement depending on how you're using it, and one implementation may be better than the other. But from the user's perspective, the same function is there. There is self, there is O distance. So if I take a point and I ask for O distance, I get the distance from the origin, whether or not the point is represented using xy or r theta. Now, of course, using O distance is r theta is good for O distance. It's not very good for translate. If I want to translate a point by delta x delta y, I have to convert the point back from r theta to xy using x equal to r cos theta and y equal to r sin theta. Then do x plus delta x, y plus delta y, and convert it back to r theta. Right? So you pay a price in one function or the other. With the xy representation, translate is better. With the r theta representation, O distance is better. And this is a very typical case of the kind of compromise that you have to deal with. You have to decide which of these operations is likely to be more common and more useful for you to implement directly. So if you think translate happens more often, it's probably better to use x and y. If you think the origin from the distance is more important, it's probably better to use r and theta. So often there is no one good answer. Right? It's not like saying that a heap implementation is always better than a sorted list implementation for a priority queue. There may be trade-offs which depend on the type of use you're going to put a data structure to as to which internal implementation works best. But what you have to always keep in mind is that the implementation should not change the way the functions behave. To the external user, the function must behave exactly the same way. Right? So in this particular example, just to illustrate what we have said again, we have changed the private implementation, namely we have moved from xy to r theta, but the functionality of the public interface, the functions O distance, translate, etc., remain exactly the same. Now we have seen earlier that in Python functions, we can provide default arguments, which makes sometimes the arguments optional. So for instance, if we want to say that if we don't specify the x and y coordinates over a point, then by default the point will be created at the origin. So then we can use a equal to 0 and b equal to 0 as default arguments, so that if the user does not provide values for a and b, then x will be set to 0 and y will be set to 0. So for instance, if we want a point at a specific place 3, 4, we would invoke this function, this class. We'll create an object by passing the arguments 3, 4. But if we don't pass any arguments like p2, then we get a point at the origin. So the function init clearly looks like a special function because of these underscore on either side, which we normally don't see when we, or normally don't think of using when we write a Python function. As we said before, Python interprets init as a constructor. So when we call a object like p equal to 0.54, then this implicitly calls init, and init is used to set up self.x, self.y. So the internal representation of the point is set up in the correct way by init. So init is a special function. Now Python has other special functions. So for instance, one of the common things that we might want to do is to print out the value of an object. What does an object contain? And for this, the most convenient way is to convert the object to a string. So the function str normally converts an object to a string, but how do we describe how str should behave on an object? Well, there is a special function that we can write called underscore underscore str. So underscore underscore str is implicitly invoked when we write str of o. So str of an object o is nothing but o dot underscore underscore str. And for instance, print, the function print implicitly takes any name you pass to print and converts it to a string representation. When I say print x and x is an integer, implicitly str of x is what is displayed. So str is invoked, and str in turn internally invokes a special function underscore underscore str. So let's see how this would work, for instance, for our point thing. So if we want to represent a point, so internally we have self.x and self.y. We want to print this out in this form, the value x and the value y. So what we do is we set up str. So remember that self is always a parameter. So what it does is it first creates a string with the open bracket and the close bracket at either end and a comma in the middle. And in between the open bracket and the comma, it puts the string representation of self.x. And in between the comma and the close bracket, it produces the string representation of self.y. So this creates a string from the value. It internally invokes str on the values themselves, self.x and self.y, and then constructs these extra things, the open close bracket and the comma, to make it look like a point as we would expect. Another interesting function that Python has as a special function is add. So when we write plus, the function add is invoked. So in other words, p1 plus p2, if these are 2 points, would invoke p1 underscore underscore add p2. So what we would expect is that if I had p1 and if I had p2, then I would get something which gives me a point where I combine these two. So I get the x coordinate as x coordinate p1 plus p2 and y coordinate p1 plus p2. It's up to us. I mean, it doesn't mean it has to be this way. But if I say p1 plus p2, the function that is invoked is add. And it's up to us to define what add means. So let us assume that we want to construct a new point whose x coordinate and y coordinate are the sum of the 2 points given to us. So here is the way we would do it. We would create a new point whose x coordinate is self.x plus p.x. Now notice that self is the function associated with p1 in this case, add. So self refers to p1 when I say p1 plus p2, and the other argument p2 is the point p. So I can look at the values of p and say p.x, p.y. I can look at my values and say self.x, self.y, and now I can combine these by creating a new point, self.x plus p.x and self.x plus p.y. Okay. So for instance, if we have 2 points at 1, 2 and 2, 5, then this will return a point at 3, 7, and I must store it in a new point. So p3 now becomes a new point whose x coordinate is 3 and y coordinate is 7. So in the same way, we could have a special way of defining multiplication, and in Python the underscore underscore mult function is the one that is implicitly called by multiply. Similarly, we can define comparisons. We might say what is to be done when we compare whether p1 is less than p2. Do we check both coordinates are less? Do we check the distance from the origin is less? We have complete freedom how to define this. But we just write p1 less than p2 for readability in our program, and internally it will call the function less than, LT. Similarly, greater than will call the function GT, and there is something for less than equal to, greater than equal to, and so on. So these are all very convenient functions that Python allows us to call implicitly and allows us to use conventional operators and conventional functions in our code, so we don't really have to think of these objects in a different way when we are coding our programs. So there are several other such functions. It's impossible to list all of them, and it's not useful to list all of them at this introductory stage when you are learning Python, but you can always look up the Python documentation and see all the special functions that are defined for objects and classes.